Okay. I already made this video once, we'll make it again. Once again, must not hit record. So we're gonna do parallel now. Here's my pretty picture I already made. You wanna take a snapshot of this one and see if the next one's just as good. There it is. Okay. So we already did series. If you haven't watched the series setup yet, go back and watch that first. We're going to use the same resistors, 2 ohms, 4 ohms, 10 ohms. You can see it's getting messier, okay? And ultimately what we're going to try to find is the current and the voltage for each one of these, okay? So sometimes you'll see parallel drawn like this. Kids are starting to get louder. And sometimes it might be easier in this picture up here for students to actually see how the voltage can go to each one individually. This picture, it actually looks like the voltage would kind of like sum here, then it would split and go here and here. That doesn't happen. So you know how the current was the same for the other one? For the series, current was equal for all of them, but voltage wasn't. In this one, the voltage is same for all resistors, but the current's going to be different, so it's flip-flopped. Series, current the same, voltage different. This one, voltage same, current different. Okay, so we need to get this down into a simple drawing. So we're going to add up all of these somehow, some way, and we're going to get an REQ. We know this is 9 volts. We're going to get an equivalent resistance, just like we did on series. Now, if you recall in series, I drew it up here. It doesn't matter where you draw the resistor, okay? Now, for parallel, 1 over REQ, 1 over R1, 1 over R2, 1 over R3. So it's a bit different. So in a series, you just added up all the resistors, nice and easy. In this one, you're going to have to play around with the calculator a bit. Okay, I don't know if you can see my calculator there. Make it so you can see. So in this case, 1 over REQ is 1 over 2 ohms, 1 over 4 ohms, and then plus 1 over 10 ohms. Somebody will be like, oh, that's easy, 1 over 16. No, it's not how you do it. You have to have common denominators. So the way you're going to do this, the way I would do it, is I would use this inverse button. 2 inverse plus 4 inverse plus 10 inverse, x to the negative 1, equals. And it gets REQ is equal to 0.85, okay? And then I have to inverse that number, right? It's 1 over. So I inverse it again, and I get REQ is 1.2 ohms, okay? Oops. 1.2 ohms, right? If you don't like the way I did it, well, look, you could just go 1 divided by 2 plus 1 divided by 4 plus 1 divided by 10. Get that, and then do 1 divided by your answer, and you get the same thing. Okay? Now, I want to find what would the current be for this. I'm going to call it IT, the total current. So, if you remember, V equals IR. Right? So the I that we're talking about in this case is the total. The voltage we could also call the total if we want. And the current is total. So IT is equal to voltage divided by REQ. The voltage is 9. The REQ is 1.2, and I would be, what's 9 divided by 1.2? I bet you it's like 7.5. Now, how would I know that? Well, I already did it, and I could, I guess, do math in my head, too. I could. Amps. Okay. Now, here's the deal. Do we really need that? Well, the question asks for it, of course you need it. Okay? But do we need it to figure out anything up here? Answer is no. But it's good because we could use our answers up here and we could use this to check. Okay? So, we know that the voltage goes to each one of these the same. So, I could write down voltage 1, 9 volts. Voltage 2, 9 volts. Voltage 3, 9 volts. So what are we actually looking for? We're looking for current 1, current 2, current 3. Okay? Now how do we do that? V, I, R. Look at that. All together. V equals I, R. So I'm going to go with this over here. I1 is equal to the V. I could have V1 here if you want. Divided by R1. Sometimes I'll just write V because I know it's going to be the same for all of them. Okay? Notice I just went right to it because I already solved for I up here. I know it's V divided by R. I mean, we only have 3 variables. It's not really all that difficult to get that right every time. All right? So in this case, the voltage is 9 volts. The resistance is 2 ohms. And I get a current of 4.5 amps. Okay. Should that current be the highest or the lowest? Which one has the most resistance? This one. So the flow would be less. More resistance, less flow. Low resistance, higher flow. This should be the greatest. Okay? Let's do I2. So my volts are still 9. It's going to be the same for every single one. My REQ is going to be 4. 9 divided by 4, 2.25. If you want to write 2.25, that's fine. I'm just going to write as 2.3 amps. Oh, look. Doubled it. Current went down, right? Current was actually half because we doubled the resistance. That makes sense, right? And then the last one, I3. Okay. 9 volts divided by my greatest resistance, 0.9 amps. Paper slipped. I think I spent more time on the other one explaining. When you make a video for the second time, you probably don't explain a whole lot, or at least as much. Okay? So I found the resistance, the voltage, and the current for each one, just like I did for the series. Okay? Now, what could I check here just to make sure? Well, voltages are easy because they're all the same. Resistance are the same because they're given to us. How about these currents? If I add this up, 4.5 plus 2.3 plus 0.9, I get 7.7. Look, 7.5, 7.7. It's pretty darn close, right? It's a rounding situation. I say that all the time in class. So we can actually add these up to check, see if they add up to this. So, you know, if they don't, couple things, right? We could have messed up this, we could have messed up one of these, right? But we have some checks along the way, you know? Least resistance, most current. Most resistance, least current. Okay, that makes sense, so that matches up. And then our numbers, when we add them up, come pretty close to this. So that is the way to solve our parallel problems. Now here's the thing. How about if we have parallel and series together? And we could have some really crazy looking schematics like this, okay? But the way to solve any of these is to do it by steps, right? We actually had like one step here, this to here, and then we worked our way back, okay? Same thing with our series. If I could find it real quick. Our series, work to here, get stuff, and then go back. Okay, the more complicated they get, you're going to have more steps, but you're just going to have to follow the pattern and work your way back.